shit.
That's what I'm talking about.
Wait.
Okay, now, from the beginning.
Cool. Alrighty. Hello, everybody. Welcome to ECS for Small Things. Thank you all for coming here at 4 p.m. on a Friday. I know everybody's energy level is probably kind of dipping. You're all kind of ready to go home. But I see a full house, so thank you all for being interested in this topic. I'm going to try to keep it interesting, keep the energy level up, but I'm also not going to make you jump up and do jumping jacks or any of that kind of stuff. So, no, you're welcome. So, ECS for Small Things. I'm Vlad Vukicevic. I'm the lead engineer, Runtime Solutions. What this basically means is my team is looking at figuring out how to bring Unity into new areas that it might have been a challenge for Unity to go to before. You've heard a lot today about this notion of performance by default, where we have a lot of new techniques and approaches where the goal is to enable you as developers to bring performance into your game by default. That tools such as the ECS architecture, the new job system, the burst compiler, all of these things work together or will work together to enable you to create games in one way and to get performance by default out of this. And that's really what we want to enable, one way to design content and to write code. But along with performance by default, we want to add another piece in there, which is scalability by default. Your content needs to run not just on massive high-end PCs with millions of things happening at once, but you also want to reach different use cases, things where load time is important, things where small size is important. Maybe you want to reach areas where your users are bandwidth constrained, limited data caps, slow mobile networks. In all of these cases, the smaller package that your end result can be in, the more reach you'll have to your users, and basically the more games that they will play. So, scalability by default. We want to make sure that we let you scale up to high performance, but also scale down to these instant light experiences. How do we do that? Well, we start with the same concepts. We start with this concept of data-oriented design that you've heard a lot about if you've been in previous talks here today. We leverage this entity component system architecture, which again helps you design games and design content in a certain way that both gets you high performance, so again, the performance by default piece, but also helps you scale down and helps us optimize for the size of the resulting content, thus giving you scalability by default as well. So with a lot of the talks you've heard today, the focus has really been on performance. How do you get a million things happening on the screen at once? How do you get a million animations happening? But instead, for this talk, we're going to focus on size. Because what we've realized is that there's a lot of areas where small is really the new big, where the ability to go down tiny is really where you want to get to. So, once we realized that, we were trying to figure out how do we take Unity concepts, and how do we actually bring them down to this very tiny runtime size, very tiny final content size. There's a couple of key pieces of this. The first is that we use a pure ECS system. So there are no classic components. You don't get access, unfortunately, to Unity's current kind of powerful capabilities. But instead, we have a highly optimized, tailored feature set that will be growing over time that is focused on enabling these small use cases. The pure ECS architecture gives us a clean separation between data and code. It lets us optimize for size and performance the parts of our engine while giving you flexibility in building up complex interactions on your end in your game code. And this is kind of the main architectural piece that lets us actually scale both up and down. The next aspect is that it is highly modular. We really want you to pay for only what you use. If you don't need physics, you shouldn't have to pay the cost for physics, either in code size or runtime performance. If all you need is simple raycasts, we should give you the ability to include the capability to do just simple raycasts and nothing else. If you don't need a particle system, you shouldn't have to pay any of the cost for including a particle system. And likewise, we want to break everything down into these highly modular components. In the future, We even hope to break this down even further. So instead of having physics be a binary on or off thing, we might give you the option to say, well, I want physics with some simple colliders only. But if I want to add support for 2D chains or something like that, there would then be another optional module with its own costs and its own features. And then finally, we also do a lot of work to optimize for delivery. Building the small runtime is really not enough because the code is only a tiny fraction of the final delivered content. The assets actually take up the biggest chunk. When we talk about some of these use cases that we're looking at right now, such as playable ads and messenger games, the assets take up a bulk of the download size, 80% or more. And what we can do there is we can apply a lot of the best practices, because we're still using the Unity asset pipeline through the Unity editor, to do a lot of compression and transformations that would be either expensive or just difficult to do on your own. Because all the assets flow through the Unity editor and then into the small runtime, we can then use things that have those two things work together to, for example, split out alpha channels and compress them separately, reuse alpha masks between different sprites. All of these things that, again, it is possible to do on your own, but these are not the things that you want to be focused on doing. You want to be focused on the actual content that you're delivering. So when you put all these things together, you end up with Unity for all things small. When we talk about small things, I already mentioned two of our current target use cases. So playable ads is a big one, but also games in messenger type apps. There's been a lot of announcements this week about a certain platform opening up, and we know that a lot of you are probably interested in figuring out how can you actually use high-quality engine, high-quality editor experience to actually deliver content to those apps. These are kind of the use cases that we had in mind. But these aren't the only use cases. There are a lot of other places where having a small runtime is important. So for example, the automotive industry might be interested in having a small runtime for dashboards and things like that. So we're really looking for these capabilities to go very broad into a wide range of use cases and industries. The components of this Unity for small things. There's a lightweight ECS core. This is actually implemented natively. For web deployment, we go to WebAssembly and Asm.js. And this is what provides the core optimized memory management and ECS functionality. We take that ECS core and then we provide you with a set of modules. This is what I mentioned before. We really want to have a fine-grained separation of the various capabilities. When you turn these things on and off, this is, by the way, not the final feature set by any means. This is a snapshot of our current editor UI. Consider it programmer UI for now. But when you turn these things on and off, the actual capabilities then just don't become available when you're building your content. If you turn physics off, you can't actually go and add a collider, because otherwise you can accidentally add some component and all of a sudden pull in something very expensive without really knowing about it. But at the same time, if you've built your content with, for example, physics, you've got a bunch of colliders and things all over the place, and you turn off physics, we don't lose that data. Something in the editor just pops up and says, hey, this thing needs physics. So you can even experiment with turning off different features, like what does my game look like if I just turn off particles without actually going back and changing the data or the actual content. Each of these modules, again, it's tied into the ECS system. So each module provides a set of components. These components can be defined either in C#, which is compatible with the big Unity ECS that you might have heard about in previous talks here, or they can be defined directly in the editor through a UI that is created just for creating components, adding fields to them. Along with components, these modules provide systems. These are the things that actually operate on the data in those components. Some of these systems are provided by the runtime itself, but the bulk of them are probably going to be provided by you, because this is where you're going to implement your own game logic. And then finally, we provide the editor experience where you can assemble entities from all of these things in the same way that you're accustomed to today with Unity. So similar view, you have your components on the side, but in this case, they're just data, and you're manipulating things in the scene view just as you would today. So this is a short video of what the editor experience looks like today. A colleague of ours on the editor team built Flappy Bird from scratch and recorded it. So the original video is about an hour and just over an hour long. And this is shrunk down into about a minute and a half. And so you can see it's a very familiar experience, but with some added pieces to really interact with this ECS system. One thing you might notice here is that the preview, whenever he hits play next, it'll actually open up a browser window. So you can preview directly in the browser. We also have a nice capability where there is a live link to that browser connection. So if you open up that same URL on a variety of mobile phones, you actually get all of those refresh every single time you hit play. So you have the ability then to connect your iPhone, your Android phone, maybe a tablet for a different scale factor, and maybe your PC browser. Make some changes in the game, hit play, and they will all reload and refresh simultaneously, so you can go and see what your changes actually did. I think he's just about to start playing. Oh, no, he's doing pipe spawning. I think this is a much harder game when it's sped up like that. So, to give you kind of some more concrete examples. So this is an ad. Let's turn off the low quality filter on this. This is an ad for a game called Fastlane. The original ad for this ran on the Unity ad network, built with another HTML5 technology. And it was about 1.5 megabytes in size, engine plus the runtime assets. We had a third-party studio, a student by the name of Working Man, build this out using an alpha preview of this version of Unity for these small things. And within about 2 weeks, they had, from not really knowing about the project at all, they had something that was playable and looking pretty similar to what you see today. This end result is less than 800 kilobytes in size, compared to 1.5 megabytes of the original. Some of that is the runtime. A good chunk of that is the advanced asset optimization that we can do because we have the editor pieces in place. OK, so let's dive into a little bit more of the underlying technology. So I've mentioned this ECS thing. Some of you that were here in the talks before, you might have a good understanding of it. But ECS is an architecture for separating out your game logic from your game data. It's based around the concept of entities, and an entity is just an index. It is just a number. It is a convenient way to refer to a particular set of components. Components are data. They are value types, structs in C#. For example, you might have a component that is a health component. You would put this on an entity that has health. It would, might have a value that is its current health and its maximum health. There might be a component that is a position. You would have your XYZ position values. Maybe you have a component that is a power-up component, which participates in your game logic, where it has the power-up type and maybe the strength of that power-up. And you can build up these components on entities to really define what they do, without really considering too much about what the interactions of the components are, but really focusing on the individual pieces and how they interact with the systems. And the systems are the things that actually make the change. Systems operate on sets of components and transform data. Some set of components goes in, and the system then modifies the data in either those same components or in other components that are related to it. Let's look at some more, so for pure ECS, like I mentioned, with Unity, you have access to a bunch of classic kind of Unity mono behaviors and such. In a pure ECS world, all data lives in components. There is nothing in objects, there's nothing in globals or anything like that. Some of these components are heavyweight. So for example, you might have a component that as part of its data contains a bunch of texture data. But most components are fairly lightweight. There'll be a couple of floating point values in size, position, health, maybe an integer that says what faction or team the particular entity or enemy is on. All code lives in a system. Again, these systems take data and transform data that lives in these components. Some of these systems are heavyweight. For example, some of the ones that are provided by the runtime will do things like load assets off of disk or off the network. They will interact with the rendering of the native platform. But most are lightweight, especially the ones that are related to game logic are lightweight. They're going to be doing some math. They're going to be figuring out, well, when this particular bullet or this thing that can do damage touches something that has a health, I'm going to subtract that damage from its health. And this really lets us get to both scale, because most of these are kind of well understood chunks of code, or well optimizable chunks of code, I should say. But it can also do advanced things like parallelism and really kind of get as much performance as we can, even out of these kind of small devices. The other thing that comes from a pure ECS system is that the game loop is now defined entirely by systems. So you end up with a simple and easy to understand and observable game loop. For every frame in this example game loop, there's a system that will handle asset loading. It'll see, are there any assets that still need to be loaded? And if so, we're going to go through and load those. System that'll deal with player input. Did the user press a button or or press an arrow key? And if so, move the position of that particular entity. Shooting system, was the button pressed? Do we need to spawn a bullet? And so on. But that also includes systems that come from the runtime. So for example, things that have animation components on them will be manipulated by an animation system, or perhaps a set of animation systems that all interact to actually do animation. Particle systems will have maybe some systems that manage the emission of the particles, some systems that manage the actual individual features, like changing the alpha of a particle or moving a particle around. And then rendering, which will actually take all the things in the scene that can be rendered and will actually put them on the screen. The nice thing about this is that there's, like I mentioned, there's no magic here. You can observe this entire set of things happening, and because for each of these things, the data always comes from and goes back out to components, if you don't like the way that we do something, you can replace it. If you want to do particles a different way because you have some particular knowledge about your game that you can do some optimization, or maybe you want to spawn particles in a different way, you can do that. You can turn off our particle system, write your own. You know the types of components that that particle system is going to work with, so you can just take that same data, do whatever manipulation you like, and as long as the end result is something that the rendering system understands, as long as you feed things back into the normal kind of sprite rendering, then you'll get things on the screen. So it gives you a really nice way of understanding exactly what is going on in your game and your content, and can also help with debugging. Like if you think particles are causing a problem, just turn off the particle system. Everything else will still continue to run. If you're having issues with bullets colliding, turn off the bullet collision or the collision checking system, and just see what happens. See, try to track down where the bug is, or the performance drop, or something, by just having kind of a very nice way to see exactly what is going on in your content per frame. So let's look at some more examples of this pure ECS concept. So like I mentioned, some things are heavyweight. Because everything lives in components that are on an entity, there's no such thing as a resource. There's no texture 2D. There's no this kind of magic object that lives off, that provides this kind of heavy data. Instead, all of that lives on particular components that you can attach to really any entity you wish. But it can be helpful to treat some of those entities as resource entities, because that's where you can have some of these heavyweight things like textures and image data, and you can share them amongst anything that needs to render a texture by just referring back to it. So for example, I might have a resource entity number 1 that just has a texture on it. This is just a container for texture data. Later on, I can create 100 entities that have a sprite renderer that will then reference that entity in order to actually draw something to the screen. But because these are still full entities with any number of components on them, you can start building more things up. So for example, you can build a second resource entity that has both a texture 2D or a sprite on it. It has an audio clip. It maybe has a collider shape on it. And this you can then be your bullet prototype, basically. Whenever you need to spawn a bullet, you can just clone this, set its position, and now you have a bullet in the scene. So you can start to build up things like prefabs from a number of these kind of features, but everything still lives in this ECS world, which lets you do some nice, powerful things. So for example, during runtime, if you want to see, if you want to have a system look at every single loaded texture that is trivial to do, and you do it in the exact same way that you would iterate over anything else in your world. If you want to look at every single audio clip that is playing at any point in time, again, you can do that because it's all within the same system. You're not trying to get something from an audio manager somewhere and get some lists or anything like that. And you can combine those things. Like if you want to get a set of every audio clip that's playing that also is something that can do damage. Again, those are all handled through the exact same framework. So it gives you a lot of flexibility to both build up complex interactions, but also to debug things in your content. One of the common issues that comes up when we talk about pure ECS is that trying to figure out how to do things that are event-driven in nature becomes a challenge. And this is something that we're still figuring out. A lot of this is us still experimenting and figuring out some of the best practices in this architecture. So this is kind of an example of how you might build a drag and drop system. When you have these components, you have the option of treating some of them just like tags, to not actually have any data associated with them, but instead use them to tag other entities based on what happens to be happening right now. So if you wanted to make something on the screen draggable, you would tag it with draggable, and you would attach a drag rectangle to it to indicate where the actual drag source is. This would then be read by a drag start system along with input, and it would do the checks to say, hey, did the user touch within that drag rect? And if so, then that system would attach this dragging tag to that entity. Now, in your game code, you can then look at, are any of my power-ups being dragged right now? And if so, you can then do things to drag power-ups. Maybe you want to spawn a particle system at that point to give it, some nice sparkles or something right behind it. The drag move system would then look at, is anything being dragged, and then the position of the touch changed since the last frame. If it did, it would update the position of that thing, and then your other systems, if you set up that particle system, it would follow along with it because it's all on the same entity there. And then finally, the drag end system would look at, was the touch released? And if so, was that over something that has a drop target tag on it? And if it was, then maybe all of the dragging and all the dragging and all those tags go away, but instead you get a dropped tag on the thing, so that then you can handle in yet another system things that were dropped. So I showed that simple kind of game loop here, but you can see that the individual systems really tend to do fairly self-contained things, and that's really the idea. So you can easily consider a game loop that's running dozens of systems at a time, and that's okay, because that then lets us do the work of parallelizing and performance optimization amongst all the different pieces that are in flight. And then finally, kind of to put it all together, let's look at bullets again. So you might have an entity that you're treating as a resource. That is your bullet. It only has a sprite on it. It's got the audio clip. It should probably also have the collider on it. Actually, no, sorry, no collider on there. You've got another entity that is your bullet prototype. This is the thing you're going to clone every single time you make a bullet. So it's got a transform for the position. It's going to have a renderer, which is going to refer back to the resource. It's going to have an audio source because you want to play that audio clip. And then it'll have things that are related to the bullet. It'll have some components for velocity, some components for damage, maybe a tag component that just says, hey, this is a bullet. And then maybe it'll also, well, it should also have a collider so that it participates in physics and in collision. And then with that, there's now a number of systems that will interact with all of this to actually get the effect of being able to shoot and have the bullet hit things. So to start things off, you'll have a shooting system. This is a thing that will check for input, and if there was input, it's going to clone that bullet prototype and just kind of let it go in the world. You'll have a collision system. That collision system doesn't need to care about bullets at all. All it cares about is it looks at all the things that can collide, and it checks, is there a collision amongst any of these things that can collide? Doesn't matter if it's a bullet or if it's a wall or if it's the player. It just looks for things that can collide. And you have a damage system. This damage system is going to look at collisions, and then for things that do damage, it's going to look for collisions between things that do damage and have life. So if there is something that does damage and it collided with something that does life, you would apply that damage. Again, none of this damage or any of these really care about that it's a bullet at all, other than the initial system that set that up. And this lets you build up really powerful interactions in your games. Do you want to have a platform that does damage to the player when they jump on it? You attach a damage component to it, and as long as it's something that the player can collide with, as it would, then the same set of systems for collision and damage would then apply damage without you needing to do any kind of special logic to say, hey, this is now this magic platform. It is just a thing that happens to do damage and participates in everything else. And then you've got a number of other systems that'll do things like cleanup when things are out of bounds, audio for playing the audio, and then finally rendering for getting everything to the screen. So let's talk about writing code for a bit, because I've talked about the data portions on the component side, and I've talked about the system side, which is this new way, this new approach to writing code that interacts with these components. The first thing that you do, obviously, is you're going to design the components. And I showed an example earlier of being able to write components in C#. You can also design them directly in the editor. And this is actually a live connection between the components in the inspector and the components that you're editing. So unlike what happens in Unity today, when you go and edit a C# file, things have to recompile, and then you're going to see things in the editor. Here, if you add a new field to this destructible component, it appears instantly in everything that has a destructible component in the editor. It makes it possible to really quickly iterate on behaviors and experiment with getting the exact right design when you're trying to figure out what data to apply to your game. Currently, for Unity for Small Things, because we are targeting playable ads and we're targeting these messenger games use cases, all of those are on the web. And on the web, the default language is JavaScript. In order to get to these very small sizes, we use JavaScript as our current language for writing systems code. But this is not a JavaScript game engine. Like I said, the engine is native code that has applicability even outside of the web environment. But in order to get the really tiny size for web deployment, we currently use JavaScript for the systems language. That JavaScript, though, you're not interacting with a whole bunch of web APIs. You are instead still interacting with that core ECS system. So you're still manipulating components, creating and destroying entities, setting and getting data. So you're still doing things in a very kind of ECS way, even though it is running in JavaScript. In the future, though, we plan to introduce the ability to use high-performance C#, which is this dialect of C# that I believe Andreas introduced at a talk earlier today, that is really optimized for writing this type of systems code. Very highly data-driven and also very highly optimizable. The burst compiler technology that we're developing, along with getting us the massive performance wins because it goes straight to native, it can also let us go straight to WebAssembly and straight to ASM.js. So in the future, you'll be able to take the exact same systems code that you might use on a large Unity project and reuse some of that code in a small Unity project without any changes, using the exact same C# code. So our goal is to let you define components and systems in C#, and then really to choose what your deployment model is. Do you want all the features of Unity? Do you want to make massive AAA titles or even the next awesome mobile game? You can use Big Unity, get all the features there. Are you looking for something that has a more optimized feature set for actually going small? Like if you need to deliver content in less than a megabyte, if you need download times to be measured in seconds instead of in minutes, then you would choose a small runtime. But the way that you develop that content and the code that you write should be the same. And we want to enable you to share assets, the data and code, regardless of what you choose for deployment, to really give you that ability to scale, regardless of what type of content you are developing. All right, so let's talk about deploying content for a bit. Initially, again, for playable ads and messenger games, we are targeting the web as our deployment model. So currently, when you build one of these projects, you get the core engine runtime and your content all packaged together, ready to be deployed either as an ad or potentially in some kind of web container for a full game. That's our initial target. That's how we're using to prove out a lot of this technology and kind of figure out what the missing pieces are as we go beyond. But because the runtime is native, it enables a lot of deployment flexibility. So the same runtime can be built for the web, like we've just talked about. You can also build it natively for Android and iOS. You can build it for other platforms, desktops, embedded systems, wherever you may be. But the content that runs on there is exactly the same. The content is portable between the different runtimes. And we go even one step beyond this. The runtime can even be embedded inside other native apps or even inside other web apps. So you might have the ability to take this small Unity runtime, embed it in a native Android app, and be able to dynamically push content to it. Again, the same content that you were running before, whether it was all packaged together deployment or natively, push this to an embedded runtime running within a totally different app in order to deliver dynamic content to your users. And then even beyond that, the content itself can either be static, it can be bundled with the runtime or bundled with your app, or it can be streamed. Again, the separation between the data and the very clean-cut code in the systems lets us actually stream additional systems and additional content. We're targeting JavaScript initially, so we can then leverage the JavaScript runtimes that are already present on all of our mobile devices in order to get new code running in a web-like environment, but still targeting this native code underneath. So all of this actually gets us to some pretty interesting deployment flexibility. I picked up a smartwatch last week, and last Friday I wanted to see how this would look running on a fairly constrained environment. This is actually running within a web view on this watch. This is not actually running natively, but with no changes, the performance is actually decent. It's maybe not something you'd want to ship, and that's why it's only kind of a short, shaky clip here. But at the same time, if this was actually the runtime running natively, the exact same content would then just run faster because all of those pieces would then be native. Alrighty, so where are we at with all of this? We announced this project first at our keynote on Monday. We've been developing this for about 8 to 9 months now. And our current focus is these playable ads and messenger games use cases. We're currently figuring out what is the feature set that we actually need in order to deliver a compelling product for messenger games. And we're in closed tests with a few teams. I mentioned some of the teams that built, for example, that Fastlane ad earlier. And we're really doing this to prove out all the technology pieces. We want to prove out the small runtime. We want to prove out our rendering, animation, all of those modules that we're splitting out. But we also want to prove out the ECS approach to make sure that we can build things like, for example, drag and drop in a way that makes sense and that is also both understandable and scalable. We're looking to do broader availability of this this year, so towards the end of this year, for these initial focus areas. So again, 4 playable ads and 4 messenger games delivered in the web content. That'll be sometime this year. The other use cases will be sometime beyond, but we have a lot of interesting opportunities on our roadmap down the line. So that in a nutshell, and I realize I was probably speaking a little bit too fast. I apologize for that. That in a nutshell is Unity for small things. We've got a bunch of time for questions here. I'm actually going to bring up Etienne here, who is my counterpart on the editor side of things. He's the lead for the editor portion of Unity for small things.
Good job.
Questions?
Hi, thanks for the talk, first of all. I have experimented with ECS myself a few times. Okay, is this better? Yeah? There's a couple of challenges that arise from using ECS. I was wondering how you're tackling them. So one of the things is on web, you've got to retrieve some stuff from the browser, like your window dimensions or handle input, which is, well, it is event-based. So I was wondering, how do you tackle that? Do you have systems set up for that? And the second question is, what does the application route look like? And do you have different stages for bigger state changes and those kind of things, enabling this or disabling systems, etc.?
Okay. So the first question was how does ECS deal with interacting with the browser's environment? How do you handle getting input, loading images, and things like that? And like I mentioned, some of these systems are provided by the runtime, and they're what I refer to as heavyweight. Like, they'll actually go and interact with the platform. So for example, for getting the current window size, there is a system that is running on the HTML platform only that will read the current width and height of the window, and it'll put it into a component that the game can then access in later systems. Input and things are handled in a similar way. For the second question, I believe it was, how do you handle state changes for longer running content? So can you disable, enable systems, and so on? Do you want to take that one, talk about the scene stuff?
Sure. So basically, this is a new data format for us. So it's something that the editor doesn't support natively yet, and we're working on integrating it. So you can think of entity tables as prefabs, essentially. So we have this application flow module that lives within that system that can schedule load and unload scenes and prefabs accordingly. So you can basically just create your state machine, transition from level to level, using the same system, the same core framework that you're kind of used to in Unity, but can also leverage with Unity for small things.
Because this is a modular system, are you doing a full rewrite of the rendering engine?
We're optimizing a lot of the pieces for small, and so to do that, we're trying to use as much as possible the workflows that Unity already provides, because a lot of the tooling is really in the editor. The actual runtime rendering portion is relatively small. So for some of those things, we're rewriting them. For some of those things, we're collaborating with the other Unity teams to make sure that their code can actually run on this other platform. And
does it support 3D?
3D is not on in our plans initially for the messenger game stuff, but obviously it's something that we plan on doing.
Yeah, kind of related to that, like, is pure ECS seems really useful. Is the plan to kind of start with this tiny Unity thing and then expand it? Like, is this how we're going to be writing Unity games in 5 years or 10 years or whatever? Like,
well, you'll be writing Unity games using ECS. I mean, the focus of most of the talks today was really about introducing this ECS data-driven architecture. So right now, these are separate streams because we have a particular use case, all these small things here, that is slightly different from the use case that the ECS work going on in Unity itself is, where they're really focusing on high performance. But the plan with things like burst and actually getting back to C# code is that these two things will unify in the really not too distant future. We need to do some additional technology development in order to get there, but this is definitely our plan. We want there to be one way to write and design content and then be able to choose, do you want to go small or do you want to go big?
awesome, thanks.
No more? Okay, cool. Well, thank you very much. Thank you for coming.